We're going to continue on here. Organicness. Yes, chapter 11, they say. After much delay, we got into organic chemistry here. So remember, as we talked about last time, organic chemistry is really kind of the study of carbon-based compounds. And pretty much most organic compounds have sort of this arrangement. It's really kind of carbons attached to carbons, and attached to those carbons are usually hydrogen. And as we talked about, and we'll talk about in these chapters, along the way, we may substitute out some of these hydrogens for other elements, which will make different types of organic compounds. But the basis of pretty much all organic compounds is really carbons attached to carbons and hydrogens attached to those carbons. That means carbon does play a central role in organic chemistry. And as we talked about, it's also really important to remember the octet rule and the idea that pretty much carbon will continue to make bonds until it has 4 bonds around it. Remember, we don't want to go over 4 bonds with carbon ever, but it will continue to do that. As we touched upon last time, as we will talk more about today as well, pretty much that's the idea when you're drawing certain structures is at the end, you may draw everything that you need in terms of all the other elements. And what's left, and usually what you sort of put on your structure at the end, are hydrogen. And you put on hydrogens enough to get it to 4 bonds. So for example, here, everything else would be assumed to be hydrogen in this case. That also brings up our good friend hydrogen, as we talked about. Remember as well, it only needs 2 electrons. And again, just like when we did Lewis structure, should always be on the outside. Should pretty much look just like that. Again, should never have dots around it, never double bonded, never triple bonded. Pretty much just a single bond to the hydrogen on the outside is typically what we have going on. In terms of the organic molecules, we talked about alkanes really, and alkanes are like the simplest organic molecules you could have. Their functional group is really like the carbon-carbon single bond. They're all single bonded. And remember, as we'll talk about as well through these chapters, functional groups are really the part of the organic molecule that makes it a specific type of organic compound. It is also, as we'll see when we talk about reactions and stuff like that, pretty much where everything occurs in terms of any type of reaction that occurs, always at those functional type groups. Alkanes have a general formula of CnH2n plus 2, N being the number of carbons there are. So if we have 1 carbon, we would have 2 times 2, which is 2 plus 2 is 4 hydrogens, and that is methane. If we have 2 carbons, we would have 6 hydrogens. That is ethane. If we have 3 carbons, that would give us 8 hydrogens, and that is propane. 4 carbons will give us 10 hydrogens. That is butane. 5 carbons, 12 hydrogens is pentane. At this point, about 5 and on, we kind of just use like prefixes, kind of like what we did with type 3. 6 carbons would be 14 hydrogens. 6 is hexa, so that would be hexane. 7 carbons is 16 hydrogens. That would be hepta for 7. So that is heptane. 8 carbons would give you 18 hydrogens, octa for 8, and that is octane. 9 carbons gives you 20 hydrogens, nona for 9, which would give us nonane. And 10 would give us 22, which would be decane. These are all alkanes, ANE. That is the way that all of these basically end with the ANE, and that's how you know it. We talked about last time, but again, just to reiterate, the faster you know these 10 and their formulas and the names, the much better off you're going to be through your organic journey. as everything really does sort of come back to these 10 names, and we just kind of, again, change little things along the way. We also talked about sort of formulas. We could have our expanded formula where we basically draw out the hydrogens. We could have our condensed formula where we basically do not draw out the hydrogens. We could have our line structure where we don't draw out anything but lines, basically. Remember that each of the ending points are carbons, each where lines come together are carbons. Anything else that is not drawn there, it's assumed to have the appropriate number of hydrogens for the carbons there that are drawn. And obviously we could just have our C3H8, which is just our molecular formula. So those are several different formulas that are commonly used in organic chemistry. We got into really just sort of naming there at the end, and we had some weird one I drew, I think. Won't be the first one, I suppose. But when we do name alkanes, there's several things that you want to sort of follow when you go about naming any organic compound, for example. And we do follow the, in most cases, the IUPAC way of naming, which is the International Union of Pure and Applied Chemistry. That's sort of like the formal way of naming things, and sort of the way most of the time that we name organic compounds. As we'll see as we go through these chapters, organic compounds have a lot of names for the same thing. They have kind of like the IUPAC name. They have like common names sometimes, and they have like historical names, all for the same thing. For example, you could have 2-propanol, isopropyl alcohol, and rubbing alcohol. They're all the same thing. There's all 3 different names for the exact same thing. So that happens a lot in organic chemistry, that like the same thing has 3 different names or multiple different names depending on sort of what it is. But most of the time when we go to name things, we do try to follow the IUPAC rules, which again is a little bit more of the formal way of naming everything. All naming pretty much starts with finding the longest continuous carbon chain. So as we talked about, when we look at organic compounds, sometimes there's a straight chain where, the carbons just go straight in a row. Sometimes there's branches that come off of that straight chain, and that's sometimes referred to as a branch chain. There's also cyclic guys where they make more like ring type structures. So there's a lot of different ways that longest continuous carbon chain can be. It will not always be necessarily the straightest one. It could go straight, go up, go over, and stuff like that. The only thing, as we talked about, that you cannot do is backtrack. So you kind of have to go one way until you hit a dead end and figure out how many carbons that is. And then you could try all different options. And you really should sort of look and try all your different options, because sometimes you might be surprised. There's like a hidden one that kind of goes in a weird direction, and there's a lot more carbons than maybe you think. So once you find sort of the longest carbon chain, in our case, it will probably match one of those 10 alkanes that we talked about. And that'll be sort of like the sort of the base there of your name, of what you're going to name. Now, once you sort of determine that longest carbon chain, there will be other what are referred to as groups. And groups are not part of the longest carbon chain, but they're attached to the chain. So everything that's not counted in your longest set of carbons in a row, everything else is considered a group. Groups, as we talked about, there's a couple of different types of groups, but a lot of times you'll have what are referred to as an alkyl group. And that is a carbon-based group. And that is also based off of those first 10 alkanes. So last time we saw this guy, which is CH3, and that's basically 1 carbon with only 3 hydrogens. And because this is based off of one carbon, it is based off of methane, which is one carbon and 4 hydrogens. It is, as we talked about, missing one hydrogen in this group, and it's missing one hydrogen in the group, so it does not end up with too many bonds, and it has a way to bond into that longest carbon chain, and that's why here we're kind of missing that hydrogen. And because of that, we dropped the last part of the name, and because these are alkyl YL groups, we basically add that to the end of the name, and that is known as a methyl group. If you had a 2-carbon one that's missing one hydrogen from ethane, it would be an ethyl group, a propyl group. Again, they will basically be like the first 10 alkanes, missing usually one hydrogen, which allows it a place to basically connect in. So we want to identify the groups that are attached. We got our longest carbon chain. Then the next thing that we really want to do is number the longest carbon chain. Now, usually, you have carbons, you usually have 2 directions which you can number. You can either number kind of left to right, or kind of right to left is basically your options there. And it is nothing more than just putting a number on each of the carbons, basically 1 through however many carbons that you have. Now, when we're dealing with alkanes and we want to basically number the chain, we always want to give the priority to the groups that are attached. And we want to give them the lowest set of numbers. So for example, if you went left to right and you had groups at carbon 2 and 4 versus right to left where you have groups at like 3 and 6, then you would want to go the way with 2 and 4. It's as simple as 2 is less than 3 is basically what you want to look at. Now, as was I think the question towards the end last time, if you happen to get a tie in each direction, and it doesn't matter which way you go, each of the groups basically have the same set of numbers, what you would want to default to is really the next thing, which would be alphabetical in terms of those groups. So alphabetically, whichever way gives the alphabetical guy the smaller number. In that case, if you tie, that would probably be the way that you would want to number. By the way, once you lock in your numbering, you can't change it. So once you decide I'm going left to right in my numbering, all the groups get numbered accordingly, however many groups you have attached there. As soon as you sort of lock that in, that's how you basically number everybody else. Once you have your number, you got your groups, you got your base of your name, you're basically going to put it together here, and you're going to put the groups in alphabetical order first, and that is regardless of any numbering. So even if alphabetically the guy that should come first has a larger number, it doesn't matter. So it is based on the name of the group, and that's regardless of any prefix. So you would not look at the prefix if it happened to have a prefix. We'll talk about that here in just a second. And then we do the base of the name. We do a couple of special things here. For example, we do between a number and a letter, we do a dash between those two. We also do a dash between a letter to a number. And if we have 2 numbers that go in a row, we put a comma between the 2 numbers. Naming is all about pretty much telling everybody where you can find everything. It's pretty much what it is. It's all about location. You're just basically telling everybody, hey, if you go to this carbon, this should have a methyl group on it. Or if you go to this carbon, this will have a chlorine group or whatever on it as you go through it. Halogens, by the way, which are also groups, they're named chloral, fluoro, iodo, bromol for those type of guys as well. Any questions on that there? Now, if you have more than one of the same group in a particular compound, so if you have more than one of the same group. So for example, we'll just do that here. So in this case, we have longest carbon chain is 1, right? Which would be methane. We have a chlorine group, we have a chlorine group, and we have a chlorine group here, right? And that is 3 of the same group. So that would be known as trichloral. And the tri means that there are 3 chlorine groups. Now, the tri does not necessarily mean that all 3 are on the same carbon. It doesn't matter. They could be on 3 different carbons. They would still be called trichloral in this case. It just means within that compound, there are 3 of the same groups. If you have 2 of the same groups, you would use di. If you have 4 of the same groups, tetra, and so forth. So we sometimes will use prefixes. So this is what I was talking about. If you had multiple groups alphabetically, here we would look at the C, not the T for alphabetical. We would ignore the prefix in this case if we obviously had multiple groups that are going here. So the tri here, again, doesn't necessarily mean, although in this case they are all on the same carbon. It just means that there are 3 in the actual compound. Doesn't mean that they will end up in the same carbon. By the way, if they were on different carbons and we had more carbons, you would have to give the location of each of those. So for example, you know, if you had, make that a carbon, not a chlorine. We'll put the chlorine up there. So let's just say we have this and we just say, I'm not going to draw everything. We'll just call it propane. And obviously here we still have 3 chlorines, right? So this would still be trichloral. We would have to give the number for each of those. And it would be, we'll just call this 1, 2, and 3 in this made up example, not fully drawn. This would be somewhere where you would use your comma, like 1, 2, 3, trichloral. You would have to give the number for each of the locations. By the way, if they happen to be on the same carbon in that case, you would have to give the same number multiple times. Like say you had 2 of them on the first guy, you would have to do 1, 1. So even though they're on the same carbon, you have to give the number multiple times. So that is where we have, you know, you might come across using some parentheses or commas here between 2 numbers, is if you have to use multiple numbers in a row and stuff like that. Any questions on any of that there? All right, so we're going to do more examples as we go through here. Let us talk a little bit about cycloalkanes as well. Cycloalkanes are cyclic alkanes. They basically are straight chain alkanes where basically the ends just kind of come together and bond. So as we can see here, that's propane, which is this. And basically these 2 guys decide to make a bond. And one of the things that we talked about last time is every time you essentially make a bond in organic chemistry, you do have to sacrifice basically 2 hydrogens to make room for it. Otherwise, you'll have too many bonds to it. Obviously, the way I just drew that, if that was going to just bond like that, each of those carbons would now have like, you know, 5 bonds, which is obviously way too many. So what happens when we do that is we will lose a hydrogen off of each of those, will come off basically. And that's going to allow those guys basically to come together. And when they do, they will make this guy here where these are typically our geometrical type shapes. Most of the time they are drawn in line structure. And it's like a triangle, basically, in this case. Each of these guys here, once again, are carbons. And each of them have 2 lines coming in, right? Which means to get carbon to 4, each of them has 2 hydrogens as well, right? And that's what we see here. This would be more of the condensed type structure for that. And again, the line structures are typically just geometrical type shapes. They are also, surprisingly enough, named after the alkanes. So this has 3 carbons. 3 carbons is propane. This is a ring type structure, which is a cyclic alkane. So you put cyclopropane would be the name of this guy. You basically just put cyclo in it. These guys actually have a general formula of CnH2 times N. It does not have the +2 because they lose those 2 hydrogens when they close up. So these guys will have 2 less hydrogens than the alkane, the straight chain alkane will have, because again, they sacrifice it when they close it up. Something we also talked about last time was the idea of saturation, right? Saturation is where we have basically the maximum number of hydrogens that are possible based on the number of carbons. And again, these guys would lose a couple of hydrogens as the guys close up on each other. So our most common ones are our triangle, which is our 3, which is our cyclopropane, our square, which is 4, which is cyclobutane, our 5-member guy, which is based off of pentane, that is cyclopentane, and our 6-member ring here, which is based off of hexane, and that is cyclohexane. Again, each of these, we don't usually put the little dots, but each of these are carbons, and each of these will have the appropriate amount of hydrogens to get to 4 for each of these guys as you go through it. And again, each of these are going to be lacking 2 hydrogens from that straight chain as they kind of close in to make that ring. Here is the condensed formula, as you can see, but I would say probably most of the time, you probably see those guys drawn in more line structures. Very, very common way of drawing them. Any questions on that? All right, so give the IUPAC name of this guy. So how many carbons the first one got? I don't know. Let me see. We got 1, 2, 3, 4, 5, 6, 7, and 8. There's nothing else drawn there, right? This is line structure. So we know that that's going to be octane, right? If there was something else drawn, they would draw it and you would see it on there. Over here, this guy is 1, 2, 3, 4, and 5. This is a ring type structure. So that is based off of pentane. So cyclopentane. Yeah. By the way, if I throw that on it, what would that then be called? Cyclopentane. Wearing a hat. I don't know. What is that line? What's at the end of that line? There's nothing drawn there. What's at the end of the line? It is a carbon, right? And that carbon has 1 line coming to it, which means how many hydrogens should it have? It should have 3. So that's actually a CH3 is a methyl group, yeah? So if you have a lonely line in line structure, nothing drawn at the end of it, it's a methyl group, right? And basically we would just add that to the name. So this would be methyl cyclopentane when you add the little line to it. In this particular case, you actually do not need to give a number in this case because there's only 1 group attached, and wherever that group is at this point is considered carbon number 1 because it would have the smallest numbering. Because if you did number it and give it a number, that's the number you would give it. So since there's only 1 group on there, you would only give it 1 thing. By the way, if I drew this, what would that guy then become? It would be a bromol group, right? What else do I need to do with that? I do need a number, right? And which number should it have? Well, it's 1 or 7, right? Or 2 or 7, I guess is the better numbers there. So if we went left to right, this would be 1, 2, 3, 4, 5, 6, 7, and 8. Now, if we numbered right to left, this would be 1, 2, 3, 4, 5, 6, 7, and 8. We want to go the way in this case it gives a group the smaller numbers. So we do want to go in this direction, which means the correct number for this guy would actually be 2 in this case. This would then be 2 bromol octane. Yeah. in that case, right? I feel like putting more things on it. I don't know why. All right, what happens? I like add that. Me too. I don't know either. I'm just drawing things just to say it. It does have 2 carbons. I thank you for recognizing that, because not the greatest drawing there, but there is 2 carbons on that one, which means that is what group then? 2 carbons based off of ethane. That would then be a ethyl group. Yeah, right. As we make it a YL. So now we need a number as well, right? So going left to right, my ethyl group would end up at carbon number 5. My bromine group would end up there at carbon number 7. Going this way, my bromine would end up at 2. My ethyl would end up at 4. Which way should I go? I should still go right to left in this case, right? And now my name, as I keep building off of this thing, should be alphabetical. We're going to go 2-bromol, right? Dash 4-ethyl. And this would still be octane at this point, right? Question on that there. And again, our 2-carbon group here is right there and right there, right? And this carbon right here would have 2 hydrogens coming out, right? This carbon here would have 3 hydrogens technically coming out of it. And that's because ethane is this. So it has 1 less hydrogen, right, than ethane. So it allows it to connect in. Question on any of those? Yeah.
So no matter where these groups are in the chain, it's okay to place it just as long as it's alphabetical.
Yeah, so when you go to name it, you do want to go alphabetical in terms of the groups. Again, regardless of any prefixes there might be. And also regardless, what sometimes people think is wrong sometimes is like sometimes alphabetically, the first guy may have a larger number than the next one. So they're like, wait, I shouldn't be doing like 5 and then 2 or something like that. But it doesn't matter about the numbering. It really is just the alphabetical part of it. Yep. Other questions? Why we're having fun, let's just, you know, throw a CL over here, what we would call that guy on the bottom. Yeah. So now we have 2 groups, right? We have our methyl that was there, right? And now we have our chloral group. Now we do need to give some numbering because we do have more than one thing attached, right, in this case. So we have options in terms of number. We could go clockwise, counterclockwise, and we also have options of where we want to start, perhaps. So we could start at this guy and go clockwise, which would be 2, 3, 4, and 5. That would put a group out 1 and 4 going clockwise, starting from the methyl group. We could also go counterclockwise, 1, 2, 3, 4, and 5 going in this direction. And that would put groups out 1 and 3, which seems smaller. So that seems better, right? Now, the other option would be we could start from the chloral, right? So get rid of this. We could also start numbering from the chloral here, which would be 1, 2, 3, 4, and 5. And obviously, if you go the other way, you're going to have a larger number going the counterclockwise way. And that also gives us a 1 and 3. So this is a tie. So we should probably default back to which way, you think? Who should actually get the lower number here? That is a chloral group. That is a methyl group. Alphabetically, which one should probably come first? Yeah, so since there really isn't a difference, you probably would want to give the chloral the 1 and give the methyl here the 3 in this case. And that would turn this into a, we're going to go here, a 1 chloral, 3 methyl, and this would still be cyclopentane. So once again, here it's kind of like, you know, we had some options as to where to start numbering and which way. And there really was no difference between starting with the methyl group or the chloral group in terms of 1 and 3. So then we do have that option of obviously giving the alphabetical guy the lower number. I'm going to say, technically speaking, it would be in that sense because you would want to go alphabetical. Again, I don't know if I would necessarily mark it too wrong, but you know, you want to kind of think about all those things that you're doing. Especially if you do have that option. Now, if you didn't have that option and there was no difference, there was a difference depending on which way you go, you would still want to go by whichever one will give you the smaller number. All right, any questions on any of those there that we just took this guy and had some fun with here? All right, we won't do it now. Here we go. What we got on this one here? A is now has 4 carbons, nothing else attached, which is butane. This is 1, 2, 3 carbons in a ring type structure. That's going to be cyclopropane, right? Which is based off of 3. That's a lot of carbons. 2, 4, 6, 8. Yeah, nothing else there. So that's going to be our octane. And this has 1, 2, 3, 4, 5, and 6. And that's going to be cyclohexane. Yeah, in this case. Questions on that there? All right, so we sort of jumped a little ahead, so we'll officially talk about substituents, which are alkanes that have groups attached. Groups attached are sometimes referred to as being substituents. A lot of times they are based off of those first 10 alkanes, and as we saw, we can, you know, kind of use the same name, put YL on it. Now, what happens sometimes, for example, though, is you sometimes can draw isomers or be asked to draw isomers. And what isomers are is they have the same molecular formula, but different connection. So people oftentimes, when they go to draw isomers, will sort of mess up in a sense that they will draw the picture different and think that they drew something that is different, but they actually ended up drawing the same thing. So this is why what we've been talking about is really helpful. One really good way to know whether or not if you actually drew an isomer or did not draw an isomer is you should name everything that you draw. And if you end up with the same name, you did not draw an isomer, you just drew the same picture looking different. And if you end up with 2 different names, then you most likely drew an isomer. That's all provided you name them correctly, obviously. So if you do name them correctly, that's a really good way to know that. And so what am I talking about? I'm talking about this, for example, let's just say we have this guy here. And let's just say here, I draw this. If we count up these guys, 1, 2, 3, 4 carbons, 10 hydrogens on the first guy. If we count up the second one, 2, 3, 4 carbons, and 3, 6, 8, 10 hydrogens. They both have the exact same molecular formula, yes? Are they isomers of each other? They are not isomers of each other because they're the same thing. So if I were to go name the first one, longest carbon chain is 4 in a row, which is butane, right? Now, if I go to the bottom one, although it's drawn differently, longest carbon chain, 1, 2, 3, 4, that is butane, even though it looks different. And it's a very common thing. People go, well, I'll just, you know, draw the bottom thing down, draw the other guy up. Even if I drew it, you know, like this, is that an isomer? That is not an isomer because if I start up here, that is 1, 2, 3, and 4. It's still all continuous, even though it looks different. So sometimes people, when they're asked to draw isomers, they end up drawing the same thing like 4 times. So they just kind of like, I'll move this side up, I'll move this side down, I'll move this over there. So this is what I'm talking about. If you're not sure if you really did draw an isomer or not, the best thing to do is actually just name it. And if you end up with the same name, you definitely didn't draw an isomer. But if you end up with something different, then you did draw an isomer. So for example, if we look at what they drew here, we take a look at this. Longest carbon chain on this guy is how many? It is only 3. And by the way, you could get that multiple ways, but we could go straight across and get it. We could also go straight and up to get it as well. We could start to the right and go up as well. So 3 means that the base of this name is going to be what? 3 carbons is going to be propane, right? We have this guy, which is a group, and that's a 1 carbon group, which is a methyl group, right? And that group is hanging out a carbon number. Doesn't matter which way you go. It doesn't. They both give you 2, right? 1, 2, or 1 and 2, right? So this is 2-methyl propane, a different name, right, than butane. So those are 2 isomers of each other. 2-methyl propane, if we count up all the carbons and hydrogens, still has 4 carbons and 10 hydrogens. So they are isomers of each other. So that's a really good way to know whether or not you really did draw an isomer or not, is to really just name everything you drew. And again, as long as you name them correctly, you get different names, you're good to go. If you end up with the same name, not so good to go. Any questions on that there? All right, then draw 3 isomers for C5H12. See what you come up with. All right, let's take a look and see. So really the simplest one to start with is just lay up 5 carbons in a row. So why not? Let's go 1, 2, 3, 4, and 5. Everything else can be hydrogen. So that is 1 line, which means it needs 3 hydrogens. That guy's got 2 lines, needs 2 hydrogens. Needs 2 hydrogens, needs 2 hydrogens, and this guy has 1 line, needs 3 hydrogens. So that looks good. There's 1. Yeah. So maybe we don't do 5 in a row. Maybe we do only say 4 in a row, and we lay up a carbon, say there. Now we'll put in our hydrogens. That has 1 line into it, needs 3 to get to 4. Has 2 lines, needs 2 hydrogens to get to 4. This guy has 3 lines, needs just 1 hydrogen to get to 4. That has 1 line, needs 3 hydrogens to get to 4, and 3 to get to 4. Hey, maybe not 4 in a row. Take off 1 more, and we'll do maybe 3 in a row. And we'll put maybe a couple in the middle there. That's going to give us 3 hydrogens. Guy in the middle needs no hydrogens. That's going to be 3 hydrogens, 3 hydrogens, and 3 hydrogens. You know, maybe you did. Estimates. All right, so I got a more than I need, perhaps, in terms of isomers. Now we want to make sure that these are all isomers, and let's do naming here to make sure. All right, so obviously here, longest carbon chain is 5 in a row. Nothing else there, which means the name of this guy should be pentane. Longest carbon chain on the one underneath it is how many? It is 4. You could get 4 by going straight. By the way, you could also get 4 by going that way as well if you want. It doesn't really matter. You could take the straightest one, is sometimes easier. That means 4, the base of this name is going to be butane, right? Not pentane. We have this group hanging off, which is a 1 carbon group, and that's going to be a methyl group. And I should number here left to right or right to left. Yeah, because that's going to give me a 2 versus a 3, right? If we went in the other direction. So that's going to be a 2-methyl butane. That's a different name, still has the same number of carbons and hydrogens. So these two are definitely isomers of each other. Yeah. Coming to the one top right, longest carbon chain is actually 3. Yeah. You could actually get it either way. If you want to go straight down the middle, you can as well. You can actually go straight and then up, or straight and then down, whichever way you want to go. So that's 3. That means the base of this name is going to be actually propane because it's 3. It has a methyl group there and a methyl group there. Methyl and a methyl. By the way, that's 2 methyl groups in the same compound. So that's not just a methyl, but that's a dimethyl because there's 2 of them. The location of each of those methyl groups is at carbon number 2. Yep. And we do need to give the number twice here. So this would be 2,2 dash dimethyl propane. Each 2 for each methyl group, even though they're on the same one, you have to give the number twice. Also a different name than the other 2, right? Which means isomer. Yeah. How about the last one that I struggled to draw there? How about the longest carbon chain on this one? Is 4. That is butane, right? We do have our methyl group here, and our methyl group in this case would be at carbon number. It would be 2 because in this case we would want a number right to left, right? And that would be 2-methyl butane. I feel like I've seen that name before. It's right there. Yes. So is that an isomer? As not. That's the same picture I drew here, just turned around. Just did like a U-turn, right? And switched around the other way. So this is what I'm saying. Sometimes it happens very commonly. You're like all happy with yourself, like, hey, I drew some nice pictures. I moved things around. But again, to really verify, to make sure that you really did draw something different, the naming part of it's really important. And again, just like I did there, if you hit 2 things that are the same name, you definitely didn't draw an isomer. You drew the same thing, just probably turned one way or the other and stuff like that. So that's a very common mistake. Yeah. Questions on isomers or how to draw? All right. So we talked about substituents. Again, fluoro, chloro, bromo, iodo, and these are for our halogens. So that would be if you have a fluorine, chlorine, bromine, and an iodide on one of those. That is how you would go about naming that. Now, here's a table from your book. It's some of the alkyl groups, and you can see our methyl, propyl, butyl. There are some that are some different names that you sometimes come across, and it does have to do with the carbon to where it attaches. So one thing that we could do when we look at carbons is we could classify carbons as either being primary, secondary, or tertiary carbon. And primary, secondary, or tertiary carbons are really based off of how many other carbons are attached. So for example, if we have a carbon that we're looking at, say this carbon right here in the middle, and it is directly attached to one other carbon, that is what is known as a primary carbon. So that is a primary carbon. It's basically attached to one. That is probably the easiest way to remember it is based on how many carbons it's attached to. Some people are taught to count how many hydrogens there are, which gives you the opposite number. So this is just like there's one carbon, it's primary. That's probably the best, easiest way to do it. Now, if you have a carbon that you're interested in and it is directly attached to 2 carbons, 1 and 2, that is going to be a secondary carbon, basically. Yeah. And not surprisingly enough, that if you have a carbon you're interested in and it is directly attached to 1, 2, 3 carbons, that is what is known as a tertiary carbon. So primary, secondary, tertiary. Like I said, sometimes people will teach you to count the hydrogens, which is opposite of the number. I personally think carbon to carbon is a good way to do it because however many carbons it's attached to is basically what the number is. So 1 carbon is primary, 2 carbons is secondary, 3 carbons is tertiary. So knowing how to identify carbons is important. And for example, if we look at propane, this carbon right here, primary, secondary, or tertiary carbon. That carbon is attached to how many carbons directly? It's only directly attached to this carbon, right? And that would make it a primary carbon, right? The guy that I just circled in the middle would be a primary, secondary, or tertiary carbon. It would be a secondary as it's directly attached to 2 carbons, one to the right, one to the left. And the carbon at the end here would be a primary carbon. So when we take something like propane and we wanted to make it a group, if we remove a hydrogen on one of the primary carbons, which are the end, we will get what is sometimes referred to as N-propyl, or like a normal propyl group. We're just attaching the guy at the end, basically. And that's what that is. It's basically the primary carbon, right? Lost the hydrogen, and that is where it's able to attach. Now, if we actually take away a hydrogen from the secondary carbon, we actually will get this group here. And that is where we're going to actually attach it to the chain through the secondary carbon. And this is what is known as an isopropyl group. And that's a very historical type guy. You could recognize it by CH3, CH3, the connection happening on the secondary carbon. And it's still a propyl group because it still has 3 carbons, but the connection as to where it connects to the chain happens through the secondary carbon versus the ends, whereas the primary carbon is where it attaches, and that's sort of like what is referred to as isopropyl. Same thing here. This is isobutyl. It also is actually being attached through this carbon right here. By the way, that carbon right there is, I'm sorry, it's not being attached there. It's being attached over here. But why do we have the arrow there? The first arrow I put there is which carbon there? Primary, secondary, tertiary, that carbon, by the way. That's tertiary, the first arrow I put there. Right. This is actually a primary, right, where it's going to be attached. This is isopropyl because it still has the iso group there, which is just like we see in isopropyl, CH3, CH3 group basically there, and it has 4 carbons. You will also maybe sometimes see groups, not too much in this class, which is known as sec-butyl. And that is the attachment of a butyl group through the secondary carbon. And T-butyl, would you imagine they would be attached through which carbon? T-butyl would be attached through the tertiary carbon, yeah. So those are sometimes some groups that you come across, and it's really where the attachment occurs. For us, isopropyl, isobutyl is the fanciest I think we'll probably get in here, but there are some other groups, and they have some historical names that sometimes you come across. Everything else, again, is just going to be based off of those first 10 alkanes and put the YL on it, but isopropyl, isobutyl sometimes will pop up, along with obviously our chloral, bromol, and iodo-fluoral type groups. Any questions on that there? All right, so let's talk about another important thing in addition to naming, which is, let's say we wanted to draw something. So let's just say we had a name like, I don't know, I'm going to try my best not to screw this up. We're going to go with a 2-bromol. We'll go with a 5, I'm regretting it already, 5-ethyl. And I clearly need more than 5 carbons at that point. So why don't we go with a heptane? So we have 2-bromol, 5-ethyl heptane, and we actually want to draw it this time. So we actually want to draw the structure. It could be the line structure, it could be the condensed structure, it could be the expanded structure. We want to draw one of those structures. So whenever you have the name and you need to draw it, Personally, it is the easiest thing to do because frankly, it tells you exactly what you need to do. And you should always approach it this way. If you have the name and you need to draw it, you should always go backwards in terms of how you draw it with the name. So we know that if I look at heptane, right? First off, I see ANE, which means it's an alkane. It's all single bonded. That's what that ANE tells me. The heptane part tells me, the hepta part tells me how many carbons. That's where you should start, just the carbons. I'm just going to lay up, which is why I'm regretting it right about now. That is 7 carbons. Oh, there's 6. All right, we'll go one more 7. So frankly, that part of the name is done, right? So continuing this way, I basically have 2 groups, right? I have a group at carbon number 2, which is a bromine, right? And I have a group at carbon number 5, which is an ethyl group, right? The nice thing is you're drawing it, which means you can number it whichever way you want to go. If I want to go left to right or right to left, it doesn't matter since you're the one drawing it. I'm going to go left to right, which means for me, I'm just going to put this one right here as a reference point. That's going to be my carbon number 1. So for me, that means that I need to go to carbon number 5, right? Which for me would be 2, 3, 4, 5. And I need to put an ethyl group, right? Ethyl group is a 2-carbon group based off of ethane. And if you're not sure, you could just put the C's for now if you like. And that pretty much takes care of that. I then should go to carbon number 2, which for me would be 1 over from my 1. And I should put a bromol, which is a Br. I'm out of name. Yes. I now will finish my picture because I know carbon needs 4 bonds and I have nothing else to draw, which means everything else needs to be hydrogen. Yeah? So we just need to put the appropriate number of hydrogens on there to get to 4. So a guy at the far right here has 1 line coming in, which means it needs 3. And I'm going to draw obviously right now the condensed formula. The guy next to it has 2 lines, which means to get the 4, it needs 2 hydrogens. The guy next to that needs how many hydrogens? Just 1, because it already has 3 lines coming in. We're going to go up now. The guy going up from that carbon has how many lines coming in? Which means how many hydrogens? 2 to get the 4, right? Guy at the very end up here has 1 line coming in, which means it needs 3 hydrogens. Coming back to the main chain here, this guy has 2 lines coming in. We'll need 2 hydrogens to get the 4. Guy next to it will be the same. Guy next to it should only have 1. Guy at the end there should have, there it is. Yes, I just drew it. Yeah. Question on that. Now, if I wanted to draw the line structure, you would do really the same thing. You would start with just 7 zigzags, right? So you would go 1, 2, 3, 4, 5, 6, 7. And we would do the same thing. I would call this perhaps carbon number 1. So for me, at carbon number 5, 1, 2, 3, 4, 5, I have my ethyl group. And at carbon number 2, I have a bromine, which I do need to write Br because it's not a methyl, right? So if I left that blank, it would be a methyl group. So we do have to put the Br in there. And now I just drew it in line structure, right? Expanded structure would look just like the condensed, except all the hydrogens would have lines right out to it. So actually drawing the structure is actually sometimes easier than going the naming part. But you should always work backwards. Any questions on that there? So why don't you try one here? Let's do let's do 3-methyl (6-propyl) octane. You can draw the condensed structure if you like. Going to always work backwards here when you have the name. So definitely here, octane tells us it's 8, ANE tells us it's all single bonded. So that's really just what we want to start with is our base of our carbons. 5, 6, 7, 8. Oh. All right, and once again, you could go left, right in the numbering or right to left. Once again, I'm going to call this carbon number 1 for me. If you went the other way, then obviously your carbon 1 would be on the right-hand side. Next would be at carbon number 6. There should be a propyl group. So for me, 2, 3, 4, 5, 6. There should be a propyl group, which I know is based off of propane. And again, if I'm not sure about the hydrogens, I'll just give it the carbons there first, and that would take care of that. By the way, it doesn't matter. You could draw it down as opposed to up. It doesn't really matter which way you draw it. At carbon number 3, since this again is carbon number 1, I have a methyl group, which is just a 1 carbon group. And now we're just ready to put in hydrogens at this point. A guy at the right here needs 3. We need 2. Just 1 coming up needs 2, needs 2, and needs 3. Here needs 2, needs 2, needs 1, needs 2, and needs 3 in this case. Yeah, and I missed one up on top, which is our methyl, which would need 3 as well. Yeah. Any questions on that? Yeah. It will sometimes happen that way when you're given a name and you draw it and go. If you were given the structure, you would name it different. It very commonly happens sometimes. So if you were given the structure, you would name it differently, probably, than if you were regarding the name. It happens sometimes. You'll see that here in terms of the name. You would obviously. This name will be right in the sense of what we want to draw. Yeah, and it happens a lot because people just make up names and stuff like that. But when you look at it, if you're following the rules to name it based on what the structure looks like, you would name it differently. And so it does happen a lot sometimes. Right. So obviously you would have a different name, but it is right in terms of that's the name that they wanted you to draw and stuff like that. And it will happen. You'll see it sometimes. Yeah. So definitely if you have just the structure and you want to go to the name, you should follow the rules. When you have the name, you should draw it like it is given to you in terms of the name. But what you might find is very commonly sometimes it will be like, that's definitely not what I would have named it if I were to just name it from the picture. Yeah. Would what be accepted for this? The drawing would be the drawing we're talking about. Yeah. So if you were given that name and asked to draw it, that's what it should look like for the condensed formula. If you're doing the line structure, obviously it should just be lines, and you could do it the same way. You could kind of do 8 in a row. I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I did 9. You see, you want that 9. Let's try that again. Get rid of that there. So we do our 8, and again, we go 1, 2, 3, do our methane, which would just be a line, 4, 5, and 6, and our little kind of propyl group there, something like that. Yeah, it looks something like that. Other questions? So drawing, actually, in my opinion, is probably the easiest to do because basically you're just copying what it tells you to draw, and it's pretty. Okay, let's take a look. Longest carbon chain in this case looks like just straight across. 1, 2, 3, 4, and 5. Sometimes it's helpful to put a box around it. Then you could hopefully identify what else you got going on there. So not part of it is here a Cl, which is a chloral group. Over here, not part of it is a 1 carbon group, which is our methyl group in this case. So 5 as the base of the name is going to be pentane. And now we have our choice of numbering. We could go 1, 2, 3, 4, and 5. Or we could go 1, 2, 3, 4, and 5. Should we go left to right or right to left? Yeah, because this way here, again, going to give our groups a smaller set of numbers. We would go alphabetical. So it's going to be a 2 chloral. This would be a 3 methyl. So chloral first, so 2-chloral, 3, I'll try to squeeze it in there, methyl pentane. 2-chloral, 3-methyl pentane. Any questions on that? No. Okay. So we talked about this a second ago, but again, just to reiterate, if we do have a cycloalkane, that is mono-substituted, which again just means that it has one group attached. We really don't need numbers because it will be considered carbon number 1. We just basically named the group and named the cycloalkane. So here's a 2-carbon group attached to our longest carbon chain, which is basically the ring structure here. That is 6. So that is where the cyclohexane comes from. 2-carbon group based off of ethane, and that is where we get our ethyl cyclohexane in this case. Once again, no need for a number as that's the only group attached, and wherever that group is assumed, it would be number 1, because if you redrew it, for example, like this, and through the methyl or the ethyl group over here, this would still be ethyl cyclohexane, because then you would call that guy group number 1 or carbon number 1. So because it's just one group and it's a ring, wherever that group lands is going to always be carbon number 1 for numbering purposes. Any questions on that there? Again, if there's 2, then you have to do like we did, I think, on that example earlier. You could go clockwise or counterclockwise, whichever way gives the groups the smaller numbers. And again, if it was a tie like we had, I think previously, then you would default to maybe alphabetical, whichever one give the alphabetical guy the smaller number. That's what we just talked about. All right, why don't you draw the condensed and line structure for 3-bromo, 1-chlorobutane. Why don't you also draw, I'm just going to make up again. We'll see how we do here. Let's go with a 1-chloral, 3, too many commas. Dimethyl hexane. And let's do a actually, let's do, okay, let's take a look, see how you're doing. So again, we're always going to work backwards with the name. So we'll start with the one they gave us, which is butane, which tells us it's 4 carbons. So that's what we want to start with. Again, just the carbons in this case. That takes care of that part of the name. 1-chloral means that at carbon number 1, I do have a chlorine group. I'm going to call that carbon 1 for me. So I should have a Cl there. At carbon number 3, I should have a Br. So 1, 2, and 3 will go there. Now everything else here is just going to be hydrogen. So this guy will need 3. This one will need 1. That will need 2. And this guy actually will just need 2. And that would be our condensed structure. Any questions on that one there? Line structure, similar sort of approach. We'll do 4. Again, at carbon number 1, there's a chlorine. So we do need to put the Cl when we draw it. At carbon number 3, there is a bromine, which would look something like so. Yes. Any questions on that one there? Okay. Coming to the ones I made up here, we have hexane. Again, that's going to tell us 6 carbons in a row. So 1, 2, 3, 4, 5, and 6. 3, 3. So I'm again going to call that carbon 1. So for me, 3, 3 dimethyl means that I have a methyl group on carbon number 3, and not just one of them, but I have 2 of them happen to be sitting both at the same carbon. And I also at carbon number 1 have a chlorine in this case. At that point, I have nothing left to draw, so everything else should be hydrogens. So we'll go 3 there, 2 there, 2 there. The guy right here needs none, as it has 4 lines coming in. Guy next to it needs 2, and this guy will need 2. Any questions on that one there? Same thing here if we're going to do line 1, 2, 3, 4, 5, and 6. At carbon number 1, again, we'll have our chlorine, and at carbon number, what was it, 3, 1, 2, 3, we will have our methyl groups. Again, we don't typically put anything at the end of the line because it's assumed to be a carbon and three hydrogens in each of those. Any questions on that one there? Lastly, here a little cyclobutane. So butane means 4, cyclo means it's a ring structure. So a lot of times we just draw that in line structure, which would look like a squarish kind of guy. Isopropyl is a special group that is CH, CH3, and CH3, right? So that would be our isopropyl group there. Condensed form that, by the way, for this would be, I guess, really more like this. Do that way, and then out to your. You want to go all condensed all the way across. Yeah. Any questions on that?
Line angle form.
Yeah.
Have the type of carbon.
Do you have to write out the carbons? Is that what you're asking? You don't. You could do kind of like a line structure with it if you wanted to. Yeah, and it would look something like that there with this guy connecting in, which means it has 1 hydrogen and stuff like that. It look sort of like that. So like that, yeah. Other questions? All right, a couple more to name, and so why don't you name these guys, see what you come up with here. There, that's going to leave us just our chloral group off the top here. 5 carbons in a row is going to be pentane. You could probably recognize that probably numbering right to left in this case will give our group the smaller number. So that's going to be a 2-chloral. So putting that together, 2-chloral pentane. Any questions on that name there? Coming to the guy on the bottom there, longest carbon chain looks like 1, 2, 3, 4, 5. You could also get, if you went this way, 1, 2, 3, 4, and 5. So you could go that way if you like as well. Again, as I mentioned last time, if you have the option and you got kind of a straighter one that's just kind of straight across, sometimes that's easier to see everybody else. That means over here, that's a line to nowhere, which means that is a methyl group, right? Same thing here. That is also a methyl group. That is 2 methyl groups in the same guy. So that's a little dimethyl action happening for sure. We also still have 5 as our longest carbon chain, which would be pentane. Now, in terms of numbering, again, here you could probably see left to right would be probably the better way. 1, 2, 3, 4, 5. Going in the other direction, you're looking at like 3 and 4, right? If you went the other way. So this would be 2 and 3. We do need to give both numbers. So 2, 3 dash dimethyl. Once again, di because there's 2 of them in the compound, not that they're on the same carbons or anything like that. So pentane in this case. Question on the name there. Question on how to name alkanes, draw alkanes. You need to be able to do both, yes, and cycloalkanes as well. Any questions on any of those?
What's the most like how many decades
It does depend, but probably in most cases 3 would be the most if you had something like at the end or something like that. Probably 2 in the middle if you had 2 on the same one, but it could be more than that if you had like 6 carbons and each one had a chlorine, right? Then you would have 6 of them, right? So it depends really on the number of carbons that you have. So If you had 6 carbons, it would be the same thing. It would just be hexa, whatever the group is, chloral, hexachloral, and then you just give the numbers for each of the carbons along the way. I would say probably very uncommon for us to have a ton of the same ones. I would say probably 3-ish, 4-ish is probably the most that should maybe prefixed by 2, 3, and 4, probably the most in terms of the prefixes. But technically speaking, if you had like octane, right, each, all maybe 6 of the 8 have the same group on it or something, technically you would have, that many in there. So, but probably won't happen too much, I would think, in here. Yeah. Other questions? Okay. All right, let's talk a little bit about the properties of alkanes. We talked about some of it. The alkanes are typically carbons and hydrogens, which means they're typically nonpolar. So alkanes with 1 to 4 carbons are typically gases at room temperature. Those are the ones we commonly think of as being gases like methane, propane, butane, ethane. 5 to 8 carbons are highly volatile liquids at room temperature. And that means that they will go into the gas phase really easily. So we might have talked about it as well. Because they're nonpolar, they're going to be using dispersion forces. And dispersion forces are those intermolecular forces of how nonpolar molecules basically come together, and they're super weak. And that means that it doesn't take a lot of convincing for these guys to kind of go into the gas phase and just open the bottle, and that's enough convincing for them to basically come apart and go into the gas phase. So something being volatile means, again, that it can go into the gas phase for, say, the liquid phase really easily. So pentane, hexane, heptane, octane are a little bit more. 9 to 17 carbons are liquids with higher boiling points and are found in things like motor oil, mineral oil, and so forth. Remember that as well when we talk about dispersion forces, which is essentially what these guys are using. The higher the molar mass, the stronger the dispersion force is, which means even though it's a really weak force, the higher the molar mass, there's more electrons, and there's a greater opportunity for things to interact with each other, and the actual will be a stronger, weaker bond. And what that translates to is, as you get into more carbons, more atoms, more electrons, you're going to get a stronger dispersion force, and it will result in things having higher boiling points than something smaller. So if you were comparing, say, methane to C10, age 22, this guy here would have the higher boiling point and melting point because it has a stronger dispersion force than the methane, which has only basically 1 carbon versus all 10 of those carbons and hydrogens and so forth. In terms of solubility, because they are nonpolar, they're typically going to be insoluble in water, as water is polar. So water is polar, and water wants to do hydrogen bonding, which is that relatively strong intermolecular force, and that is a bond between hydrogen and nitrogen, oxygen, or fluorine. And when a nonpolar guy like this comes along, it wants to use dispersion forces. These are 2 very different intermolecular forces, and they really don't mix. So that's why nonpolar things and polar things don't mix really well. And that's why oil and water don't mix, because oil is basically all nonpolar and water is polar in this case. They are typically less dense than water. So in most cases, if you put water and an organic guy and a water aqueous type guy, the water layer is typically the bottom layer. The top layer is the organic one because it is less dense, and you will see different layers when you mix those 2 together because they will not mix into one layer or anything like that. Combustion of alkanes. Alkanes go through 2 types of reactions. One that we're familiar with, which is the combustion reaction. And that is basically an organic guy, which is your carbon, hydrogen, oxygen, plus O2 makes CO2 plus water, and usually a flame, like when you light methane, yes, and light a Bunsen burner. are propane, butane, like your barbecues, right? Or those things, you typically get a combustion reaction, gives off flame when it goes in air. In this type of combustion reaction, always O2, always CO2 and water is typically your product. You could have a incomplete combustion where you make carbon monoxide and water, but in most cases, probably complete combustion would be CO2 and water. Here's the combustion of butane. Another reaction that that alkanes undergo are ones that are referred to as substitution reactions. And in organic chemistry, there's substitution reactions. There's also addition type reactions. A substitution reaction is pretty much what it sounds like. Something goes off and something goes on in its place. So you kind of substitute something for it. In the case of an alkane, what happens is, generally speaking, you have some hydrogens. And if you add something like a halogen to it, which is like Cl2, and this will sometimes be mono-substituted, which basically means what's going to happen in this case is any one of these hydrogens, they're all the same. They're all equivalent. So one of these hydrogens will go off, and one of these chlorines will go on in its place, and nothing else changes other than one gets popped off and one goes on in its place. So one of the first things you should learn as we go through these chapters is when you're drawing the products of these reactions, don't do anything funny and just draw what is there, because you have 90 some odd percent of the molecule that you need to draw. What I mean by that is I'm frankly just going to copy what was there, and I'm not going to change anything other than that hydrogen. So I'm just going to quickly copy exactly what was there, and now I'm going to put the Cl on. Now the H came off, and there's also another Cl. So H and Cl come together to make HCl, yes, and you get a different product as well. But this is what is sometimes referred to as mono-substituted, and that's usually in this reaction, what they're looking for is just one of the hydrogens come off. Again, you can take off any of the hydrogens in this case, it's all the same. That would be chloroethane, right, in that case. And if you do it under the right conditions, you could force off all the hydrogens and all be replaced with chlorines. But usually when this type of reaction, we're looking for just kind of the one coming off. And again, you can choose any of those. Doesn't matter also, by the way, if it's a ring. Each of these carbons, right, have hydrogens, right? Even though they're not drawn, and the same thing would happen. One of these guys would come off. This is basically two BRs together, right? One of these guys will go on. Nothing's going to change other than I'm just going to put my BR on, and now my H and BR will come together to make HBr. So alkanes can also go through substitution reactions, basically pop off a hydrogen, pop on a halogen, and again, usually just one of them is sufficient for these type of reactions that you draw. Any questions on reactions of alkanes? So combustion, substitution, yeah. Yeah, so it probably would be in this case more it's likely the gas sort of version of it, because that's ethane and it's also a gas, and the Cl2 is also a gas, so it's probably going to be both. That gas is probably be that case. Other questions? All right, then we're going to look at the next couple of organic groups, which are alkenes and alkynes. These have functional groups of alkenes are carbon-carbon and needs to have at least one carbon-carbon double bond. Alkynes have at least one carbon-carbon triple bond is the functional group there. The good news on this is, frankly, it's named from those first alkanes as well. Because they have double bonds and triple bonds, they are what are referred to as being unsaturated. which means they do not have the maximum number of hydrogens they should because they have a double bond or a triple bond, which means, as we talked about earlier, you got to lose, right, a hydrogen on each of the carbons. So for example, if we take our friend here that we just drew with all single bonds, that is ethane, right? ANE. Now, if I slap a double bond in the middle there, I got to get rid of a couple of hydrogens to do so, or I have too many bonds, and that's going to give me something that looks like this. That still has 2 carbons and a very badly drawn thing there. And it's based off of ethane, but it has a double bond. So surprisingly enough, that is known as ene, just like an alkene, ene, yes. And if I wanted to slap a triple bond on that guy, I need to remove another set of hydrogens, right, to make room for it. And we will triple bond that guy. And that is a triple bond with his YNE. That is ethine, YNE. So ethane, ethene, ethine, all based off of ethane, all have 2 carbons, different numbers of hydrogens because there's a double bond, triple bond happening here. Alkenes have the general formula of CnH2n, much like the cycloalkanes, because it's missing 2 hydrogens. Alkynes have the general formula of CnH2n minus 2. And for example, here, that is 2 carbons. 2 times 2 is 4, minus 2 is only 2 hydrogens. Guy in the middle, 2 carbons. 2 times 2 is 4 hydrogens. Any questions on that there? So they're all based off of the alkane name. They have double bonds or triple bonds, depending. They are, as I mentioned, unsaturated because, as we just talked about, again, we are losing basically hydrogens to do that. They react with hydrogen gas to increase the number of hydrogens and become alkanes. They actually go through addition reactions. We'll talk more about it later in this chapter, but these guys will go through addition reactions. For example, if I took my alkene here and I added hydrogen, which is H2, this is going to be an addition reaction, which means we're going to actually add both of those hydrogens in. Now, if you remember, when we put the double bond in, we took out hydrogens, right? How did we take the hydrogens out? 1 from each carbon, right? That's how we took it out. When we put the hydrogens back in, they go back in 1 to each carbon. So they go in just the way we take them out. By the way, can I throw the hydrogens in right now and just put the hydrogen on each carbon? Would that be okay? How many bonds would carbon have if I did that? So if I just laid up a bond to hydrogen, and I said, I just want to put a hydrogen in at each of these carbons, is that okay? That's not, because I now have too many bonds, right? So they do go in that way, but we do need to make room for it. So when you do an addition reaction like this, as we'll talk about a little bit later on in this chapter, the first thing you got to do is pretty much make room for it. So the first thing you want to do is draw exactly what is there. Everything's going to happen right here at the double bond location. You're going to draw it exactly like that, except you're going to make the double bond into a single bond to make room. So we're just going to draw exactly like it. We're not going to get fancy and make other things there. And now I have room, right? And now I have room for each of those hydrogens. And what would be left is just to put a hydrogen there and a hydrogen there. I go from an alkene now to an alkane. This is what is known as a hydrogenation reaction. And it's an addition reaction. So different than substitution where one goes off, one comes in. In this case, we're just going to add both things in, one to each carbon. We have to make room for it by getting rid of the double bond and making it a single bond. Question on that there. And we'll do some more of those a little bit later on in this chapter. Now, alkenes definitely will contain, as I said, at least one double bond, maybe more than one double bond, but it has to have at least one double bond in there to do it. It also changes the geometry of it because now when we look at this guy right here, that is 1 electron pair, 2 electron pairs, 3 electron pairs, and 1, 2, and 3 bonds. That is our friend trigonal planar, our triangular, which has a bond angle of 120 degrees. And that's different than what we saw with our tetrahedral geometry in alkanes when they were all single bonded. So we do get a little bit different of a geometry that occurs because of the presence of the double bond. In addition, alkynes also have a different geometry that occurs because of the triple bond. So if we look at the triple bond here in our alkyne, this carbon has 1 electron pair, 2 electron pairs, and also has 2 bonds. That's our friend linear geometry, which is a bond angle of 180 degrees. It actually straightens out, which is why it looks like a straight line in this case, right? As opposed to what we saw there in our trigonal planar, which looks like the triangle geometry that occurs here. So by adding that double bond and then the triple bond, the geometry of those carbons actually do change. Not crucial for us in a lot of cases, but you will see line structures show the geometry. So sometimes with a triple bond, it will just be drawn kind of straight rather than the zigzag sort of shape that occurs. So it does definitely change the geometry of it. Now, how do we go about naming these guys? Let's first identify these. First one is an alkene or alkyne. It is an alkene as that is the double bond, right? So this is an alkene. This is a alkyne, right? As we have a triple bond, and you can kind of see it's linear as well, right? So how do we go about naming these to finish up here for today? We do the same thing. We are looking for the longest carbon chain. It needs to contain, though, the double bond or the triple bond. So you can't avoid the double bond or triple bond. It actually has to contain the double bond or triple bond when you count it. So in the case of the first one, that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, 8 carbons, right? That is 8 carbons, which is based off of the alkane name for 8, which is octane. This, though, is an alkene, so it now is not octane, but it now becomes octene. Now, different than an alkane as well, when you are dealing with double bonds or triple bonds, they take the priority in terms of numbering and everything. So when we number this chain, we want to number it whichever way will give, in this case, the double bond, the smallest number. Which way will give that double bond the smallest number? Left to right, 1, 2, and 3 is where it would start. If you went the other way, 1, 2, 3, 4, and 5. So we do want to number it if there was other groups attached. And in addition, if there is a possibility of more than one place where you can lay up a double bond or a triple bond, you need to tell the person where the double bond or triple bond is located. That's usually about 4 or more carbons is where that sort of starts. So for example, this would actually be known as 3-octene. The 3 is the location of the double bond. Now, if you have this, for example, this is called ethene. Is there any other place where the double bond could be located? No, it only could be between those two. So you don't need a number. So usually around 4-ish or more is where you got to start putting the number to identify where the double bond is. This is important because now I'm just going to build off of this like you enjoy when I do. And I'm just going to lay me up a bromine right about there. What would this be called now? So this is a bromol group, right? What would the number be? I think 5 would be good because we're going 1, 2, 3, 4, and 5, right? Because we are numbering this way. We do have to number that way because that is the way that gives the group the smallest number. And once we lock in the numbering, if we have another group there, then it has to be numbered accordingly, which means with my bromine there, this would be 5-bromol 3-octene. 5 for the location of where the bromine is, 3 for the location where the double bond is. ENE at the end means double bond. Question on that there. So whenever you have a double bond or a triple bond, they always take the priority in terms of numbering. Now, you can definitely run into a situation where it won't matter in terms of the double bond or triple bond, whichever way you go, they'll end up at the same number. Then what you should do is default to the next important thing, which would be the groups. And whichever way would then give the groups the lower number. So there's kind of these things like you want to go give this guy the priority, but if it's like a tie, then you want to kind of go to the next important thing and as to which way you would number. By the way, longest carbon chain on the bottom one is? All right, so let's see. I don't know either. Let's see. I'm getting tired. That's the triple bond. So I'm going to start here. That's 1, by the way, right there on that side of the triple bond. By the way, 2 is right there. Yes. Because triple bond's linear, so it's straight. So you don't want to miss that one. That's 3. That's 4. That's 5. That's 6. That's 7. That's 8. Well, let's just make sure. That's 1. That's 2. That's 3. That's 4. That's 5. That's 6. That's 7. So perhaps 8. Yes. So 8 is like that whole thing right there. Scary. 8 is also based off of our friend octane. But in this case, we have a triple bond. So that then becomes octine. Obviously, our triple bond, we do need to give the number. It's located at carbon number 1. Seems good. That means that's carbon 1, that's carbon 2, that's carbon 3, that's carbon 4, where we have this group that's now a group, right? And that has 1 carbon, 2 carbons, and 3 carbons. So that is a propyl group, right? Carbon number 4. So that's a 4-propyl 1-octene. Yes. Very common. People miss the carbons there in the triple bond and line structure because it's straight. I've done it a number of times. So because it does kind of go, and that's what I was saying before, you can see sometimes with line structure, they will draw it more linear, kind of straight, as we see there with the triple bond. So again, there's got to be a carbon on each side of the triple bond in that case. Any questions on that? So double bonds, triple bonds, priority. Any other groups that are there, numbered accordingly based on the double bond or triple bond. Still alphabetical order for the groups. And again, 4 or more carbons, got to lay up the number for double bond or triple bond. Any questions on that? All right. Funness.